Hello, my name is Jakub Horn and this is my first demonstration of SRv6 technology. In this demonstration, we will show few very basic features of segment routing with IPv6 data plane. During this short demonstration, we will show how to create different end functions on VPP and how to use them from SRv6 capable end host. For this demonstration, we will use a very simple scenario. We will have two routers connected to the internet, and to each router we will have one end host connected. Routers will be actually instances of VPP, Vector Packet Processing. We name them blue and orange. VPP is a highly optimized packet forwarding application running on generic hardware, in our case Linux server. And on the same server we will run two containers which are SRv6 capable, red and green. In this demonstration, we will show a few very basic SRv6 functions. First of all, Linux hosts will encapsulate IPv6 packet into another IPv6 packet with SRv6 header. Then adjacent VPP will always do what we call end function. So it will use information contained in segment routing header to forward packet through the internet. And finally, remote VPP will always do decapsulation of IPv6 packet and forwards it towards appropriate host. So let's start. We have two servers and we need to connect to them. Each one is running different version of Linux, and there is slightly different version of kernel as well. As a first step, we will need to start VPP on each side. And connect to it. By default, VPP acquires all unused available physical interfaces for itself. On each server, we had one spare interface available for VPP. In this scenario, gigabit interface B00 and gigabit 401 are connected to the internet in different locations. We will do proper addressing and unshared interfaces on both sides. VPP is plain forwarder, and here we do not have any control plane. For this scenario, just one single default route is sufficient. In a real network, the same thing will be handled either by a routing protocol or SDN controller. So by now we should have full reachability in between those two routers. So now we have two routers, blue and orange, and they are connected through internet, which is obviously not capable of any SRv6 functionality. Each router has its own public IP address. Next step is to add red and green containers. For this lab setup, we will use only Linux namespaces. So we need to create namespace. We need to add pair of connected interfaces named VPP0 and VETH and S0, and VETH and S0 will be only interface assigned to the namespace. Now we need to add VPP0 interface to the VPP itself. Next step is to do proper addressing of the host and appropriate VPP interfaces. For demonstration and simplicity, we will use IPv6 addressing, which can be only used in a lab, but obviously not in any kind of internet. So we will assign addresses from the network A:/64. So VPP will get address A:1 and B:1 on the orange VPP, and same addresses from the same network will be assigned to the individual or to each container. So we need to first connect to the container and then assign addresses there. A::A for red container and B::B for green container. So we need to also add their default gateways. We will not be using the gateways which were found by router advertisement. So our topology now is following. We have two routers, blue and orange, and we have two hosts, red and green. We have proper addressing everywhere and proper simple static routing to ensure connectivity. So here is how routing table looks like on each container. And therefore we should have the reachability to the nearest VPP, which is A::1 for red container and B::1 to the blue container, to the green container. But obviously there is no reachability between red and green containers, as routers in the internet are not aware of any A or B networks at all. To make servers reachable, we will use SRv6 encapsulation on host to create tunnel to the far end router. So SRv6 is supported as of Linux kernel version 4.10. And on both sides we have different releases of kernel, but both support SRv6. Also, we need IP route to SRv6 capable to make proper setting on each host. Now we need to enable SRv6 functionality on the routers. For this demonstration, we will use end behavior to simply move packet along the segments, and then end DT6 functionality and end the X6 functionality to decapsulate packet. First, we will establish end functionality on each router, and we will select address from correct range, which is routed towards each VPP. So we have established a local seed on the particular address, which is routed towards VPP blue. and same thing we need to do on VPP orange. End behavior is plain end of the segment functionality, which terminates one segment and start the new one. And DT6 function will do decapsulation of the packet and then table lookup in appropriate table. So on VPP blue, we will establish DT6 functionality address from the same range, and 1 at the end of the command means actually index of the table to do proper lookup. On the orange VPP, we will use cross connect directly to the interface towards the green container. So no lookup here is performed, so we don't need to add any table. We just need interface and the next hop to achieve layer 2 encapsulation. SRv6 functions have to be established on globally routed address in this example, as they will be used for forwarding purposes over the internet. Last thing here is to make sure the containers will properly encapsulate packet destined to the other container with correct list of segments to get through the internet and reach right destination. Same way we can use low latency pass or pass through virtual function or whatever. It is done simply just adding IP route towards the destination with appropriate list of segments, which are supposed to be end segment on the near VPP and NDT6 or NDX6 on remote. So first of all, we need to connect to this container red, create the route towards the B://64 via default gateway. Encapsulation is segment routing v6, mode is encapsulating, and the segments are the local VPP end functionality or end behavior and the remote VPP and the X behavior. On the green container, we need to do same thing, just opposite, and we need to use and the X function on the blue router. Okay, and now both containers should have reachability. So let's verify that. And we can even take a look on the packet. So this is how packet forwarding looks like from red to green. Red will take original IPv6 packet from A::A to B::B and encapsulates it into new IPv6 packet with SRh. Source address remains the same, so A::A, but destination address is taken from SRh active segment. Active segment is end functionality of VPP blue. VPP blue will do end behavior, which means decreasing segments left by 1 and copy active segment into destination IP address. This is NDX6 of orange VPP. Then packet goes through the internet, and based on active segment, it will reach orange VPP. Orange VPP will do NDX6 functionality, which actually means decapsulation and forwarding of original packet to the configured cross-connect interface with appropriate layer 2 encapsulation. So on link towards green container, we do see only original packet A to B. And this is exactly what we do see here. We captured 2 frames, and first frame is purely IPv6 frame coming from A to B, and it's ICMP echo request. Whereas the second frame is echo reply with the source destination B to A, but we do see the outer IPv6 header is actually from B towards the end functionality of the Orange VPP. The next header here is 43, and this is a routing header, and the next header of the routing header is again IPv6. So there is second IPv6 header, which is ICMP packet. And that's it from my side. Thank you for your time, and looking forward for it in the next SRv6 demonstration.